So good evening, everybody. So my name is Alessandro Luzio. I would like to thank Antonio for including me in this environment. For me, it's new, and I'm really excited to be here and interested in all your fields today. I'm gonna propose. I come from IIT, from Milan, Istituto Italiano di Tecnologia. We develop nanotechnology as a fact. And today I'm gonna show you what we are doing in the field of edible electronics, and precisely that we are developing a smart pill which may enable continuous gut monitoring, which is a tool that I believe that may be of interest for this community. And that's why I am here. So first of all, the basis of my research is edible electronics. What is edible electronics? Edible electronics is a kind of electronics which is 100% safe for ingestion. Okay, so it's not based on silicon, indeed. And we define it edible because it obviously have a function, it finishes function, and after this, in part, it gets digested, and in part, it's excreted with the faces. So exactly the same fate of the food. Why should I eat an electronic device? This is something you can imagine, because we need tools that can allow monitoring or diagnostic to the gastrointestinal tract. That may also allow smart drug delivery, for example, but also the tracking of medication adherence is a thematic, which is kind of hype in these days. It is something that already exists as a fact. It's called ingestible electronics and comprises standard electronics for the most, and also standard batteries. What is the problem with ingestible electronics? Not a big problem, as a fact, it's a very established domain, including standard electronics components, which are very powerful. There are high performance and very advanced functionality with this kind of pill. I think some of you know it. One was also produced quite close to here, a Medtronics company, and now it's discontinued. And it's obviously limitedly invasive. At the end, it's much better than any gastroscopy that you can do, as you can understand. And it's biocompatible in the sense that the shell of this electronics is totally biocompatible. But at the end, it's quite expensive. So you cannot use it every day. And there is a non-zero risk of retention, which means that in case it doesn't go out, you need to go to the hospital and be probably go through a surgery to remove this. And this means that you cannot really administrate yourself the pill, but you need to do it under medical supervision. And indeed, you cannot imagine a high diffusion of this kind of pills because it's standard electronics and it would have an high environmental impact. So the idea is to use it mainly for occasional use, which is advanced diagnosis of gastrointestinal diseases. We are proposing today an emerging field, something new. So at the end, as a fact, it's still limited in performance, and it's fully made of edible electronics components, which means that it's zero invasive, it's totally inexpensive, and I will show you why, and it's 100% safe. And this opened the way to non-supervised self-administration, so something that anyone can use at home, buy in the pharmacy and use at home. And obviously, you can imagine that you can do its food mainly, so it's totally biodegradable, so has a very limited environmental impact. So why is different? Because this can be used as a daily monitoring tool for the early detection and prevention, which is something I've heard a lot during this conference. And as a fact, not only for gastrointestinal disease, we can try to monitor metabolic disease, also nutritional disease with these kind of things. And indeed, we can also imagine to make a hybrid, waiting for developing the real edible electronics, which may be a good way to go to the market quite easily with something with very good impact. And just I just added for you just to convince you that this can be helpful for your community. I think these kind of tools may be interesting because we can try to help in mapping microbiota, but also in setting personalizing diets to support cognitive function, also monitoring gut health in IBS and IBD patients, and so on. I mean, you can read yourself. I mean, this is just to say that I'm quite convinced that this is something you may be interested in. And how to do it? So we started with an ERC project something like 5 years ago. We are quite pioneering this field, so don't expect to have the product now. There is time to be waited. Our idea is to use the functional properties of food, electronic functional properties of food, which means that semiconductor, conductor, and insulator, which are the main categories for electronics, are directly taken from foods and food additives, which means any material which has been regulated by EFSA, for example, in Europe, which is an agency where provide materials with DRV, RDI, and ADI. So we are sure that at least from a material point of view, the edibility is provided. And why I was telling that this for us is also a way to do inexpensive electronics, because as a fact, we use printed technology. We started from printed technology. As a fact, we are a group that is a very state-of-the-art in printed electronics, which means that you can formulate inks with functional properties, and the printing technology compared to standard electronics is very inexpensive, because you can understand you can have high throughput, low power consumption, low material consumption, very low cost and versatile facility, so no more a plant. And the technique is simple, it's purely additive. This is something that may not be familiar for you, but you can believe me. And indeed, what is important also is that compatible with very large area, light, stretchable, conformable substrates, not only rigid, which is a limitation for edibility, because rigid substrate may cause some serious damage to the intestine. And so also biocompatible, obviously biodegradable. And this is just to convince you that we are almost there with this. These are advancements that we have done also in our lab, actually. So we have reached some frequency, which is now okay for data communication, Wi-Fi data communication, I mean. So we are also able to do very ultra conformable device. So something that can really have an intimate contact with a surface, with a biosurface, for example, and we can really interact with the surface. And also, this is just to demonstrate that we can also do any kind of physical sensing using molecular electronics, which means that you can actually do molecular design and define the molecule in a way that it can sense temperature, pressure, or any kind of physical parameter that you may be interested in, but also biosensing, as was demonstrated lately by this Nature Biomedical Engineering for the detection of, I think it was for COVID. And indeed, it's a very, very realistic chance for sustainable electronics, as demonstrated by the last advancement in this field, in which circular economy pillars have been included, like the full biodegradability of the device, or the application of purely green synthetic rods and processes for our inks and for our materials, and at the end, the possibility also to be biosourced, to go to a biosource of our materials, like the example I reported here. This is just to demonstrate very fast that, as a fact, organic electronics, printed electronics is going in that direction, which is going to be more and more important, especially if we are imagining to develop a tool that need to have a high impact in the market, so to be highly developed and have a big production. So this is just to mention the product where I've been working so far. So electronic food and applicable electronic system for biomedical and food monitoring applications, so the ELFO project. And we have adopted a systemic approach in this. So we've been working on each part that we may consider fundamental to produce a real prototype of an edible electronic device. So the sensor, the power supplies, the communication, which is fundamental indeed, but also the materials that we need for sensing and for the micro and optoelectronic components. The main part, I mean, the main choice that we did for our electronics to make it effective is to mainly rely on intra-body communication. So to use the conductivity of our body to communicate the signal from the intestine or from the gastrointestinal tract to the outside. So using an external patch as the detector and using the pill as for signal generation. And obviously, you can play between different regime of coupling between the patch and the pill to obtain a signal modulation which is coupled with some biosensing phenomena, for example. And this is something you can do. It has been demonstrated. And what we gain in this way using this strategy, so don't using RFID communication, for example, for communicating with external part, as most of the actual pill are doing, but using intra-body communication is a very, very reduced pill complexity. You don't need any RFID electronics inside, which is already a big reduction. Safety is also reduced as a consequence because less electronics means more safety, and you reduce the production cost and you make it more accessible. Yeah, this is just a sketch of what you need. As a fact, you just need a battery and a signal generator and a sensing mechanism that modulate this signal. So let's start, practically speaking, what we have and what we still need, what we're working on. So we have already developed a bunch of conductive pastes, which are fully edible and are made just of food in this case, or edible material. So in this case, this paste was made of sunflower oil, beeswax, and activated carbon, and it works with a very nice resistivity, and we use it as an impedance sensor, for example, in our pill. And we also demonstrated in vitro the proof of principle that the intra-body communication is effective in in being coupled with any sensing signal, or in this case, we have been coupling it with a metformin release mechanism from the pill. So for smart drug release in this case. So you can clearly see that you can follow the mechanism of release of the metformin by using an external detector and using intra-body communication, so intra-fluid electrical signal propagation. And all these things are patent pending, so no, as a fact, it's not updated. The two of these are already patented. What we need, there is a very important activity which is in progress but very advanced, which is on the battery. So the battery is the big difference with standard technology because the battery is very dangerous as a fact. In your intestine, if your pill stay there and the battery get in contact with the fluid, it's pretty dangerous and you risk really to damage your tissues and have some burning, serious burning. So we have developed, as a fact, a battery which is already functioning. This is only made of food. In this case, you can see all the ingredients that we employed for our battery, and the main the main coupling is the redox coupling of the battery, which is made mainly of oxidized quercetin, which is a flavonoid which is highly present in food, like in capers, for example. And you can also on the other side reduce riboflavin as the other part of the redox couple, when the riboflavin is like vitamin B, so it's even more important. It's nutrient, it's not only electronically active. And by coupling with this no-resoaked algae separator and using the activated carbon as collector, and by protecting everything with beeswax, you can actually obtain a very nice discharge phenomenon, which is already useful to obtain some charging phenomena. Like in this case, we have been use a couple of these battery to power some an IoT device, a temperature and humidity sensor. Obviously, you can see they are big now at this stage of development. We are working intensively in reducing it to make it to be able to put everything inside the pill. But we are there. We are closely there. So this is something we are doing. Obviously, then we need the signal generator, because I told you we want to produce the signal inside the body. And to do this, you need to create a edible microelectronics active component, which is the very challenging part, you can understand. But this is where we are strong. So let's see what our main choices for microelectronics components. So talking about insulator, you need a substrate for sure. And basically, the best substrate are cellulose-based. And this is very biocompatible, but it's also edible. You can also biosource it using kombucha. For example, I've been hearing about kombucha today, and so it can also get some nutrient inside. And also, it has very nice mechanical properties like lightness, transparency, flexibility, conformability, and mechanical strength, and which enables also to be able to transfer it after processing the device on top of it. So it's really comfortable for many things. This is like a technology which actually resembles the tattoo paper. It's the identical approach, the one for the babies. Talking about conductors, luckily why we are lucky, because as a fact, the gold, the edible gold has been already regulated for consumption, and the gold is the best conductor that you can imagine. Has been regulated because of, I think for mostly to decorate food. no nutrient value, but still is very conductive, and for us is the best. But we can also try and mainly we process it using ink solution, inks for printing, or also using laser patterning technique, and it's quite effective. And also we use ionic conductors, so electrolytes. So you know how important are electrolytes in our body and how much of electrolyte we have. So, and this allow us to bias our device at very, very low power. So it's very key factor, the use of electrolytes like gelatin, no? It's like ketosane base or pork gelatin or any kind. And obviously the key is the semiconductor. It's like the silicon in the standard technology. So what is our counterpart in the organic world? So any material which has this kind of chemical structure is potentially, is for sure, you may know, a dye, a natural dye, a pigment, but still it's also a semiconductor. It's able to provide the same properties that make it a dye is in the organic world, make it a good semiconductor from a chemical point of view. And in nature, we can find a lot of molecules that share this kind of structure with this conjugated system we call, so an alternated double bond. And many of these are present like carotenoids, like flavonoids, like chlorophylls or the porphyrins or things like that, but still, and we also have synthetic alternatives because there are also synthetic food dyes, and we know, but the problem is that they are not chemical stable, most of them. And also, you really need to use this chemical structure, you really need to crystallize perfectly this molecule. So you really need a very ordered system which allow more charge to go from one molecule to the other, or else you will lose any electronic properties that you can expect from them. So this is where we have been pushing a lot in terms of research. So trying to understand how we can develop processes, material processes that can actually improve the microstructure, the nanostructure. That's why it's nanotechnology, the fact. And then through this improvement, use it as a fact, as semiconductor and not as nutrient. As beta-carotene is a very important nutrient, we know, we were able to aggregate it in a way to obtain very nice electronic characteristics. I will not describe it here, but also with improving the stability of this material, which are very well known to be unstable. On the other side, we can also use a different strategy using synthetic pigments and then demonstrate that they are edible using a road of, I would say, simulation first and then in vivo test. But in the case of copper phthalogen, we were very lucky because this is a very important semiconductor in our field. It works quite good, but also it's a whitener in commercial toothpaste, which means that we are already eating it a lot every day. And as a fact, we have quantified how much pigment we are eating. As a fact, we are eating something like 0.45 milligram per day, which means thousands of transistors, as a fact. And this was in collaboration with Novi Sad University, with a real dentist. So I can testify that it's true. So, and that's just to show you that this is our first fully edible transistor. It's working quite nicely and at low voltage, which really allows safety also in the operation in the intestine, because the power that can be operated in the intestine in a safe way is very limited. And it's also green because we can also recycle it, upcycle it directly from the toothpaste, for example, or for any other paste. So this is actually, we can also work with other polymer. I will not spend time. I use in vitro cascade for simulate ingestion and check as a fact. Okay, I will go fast with the demonstration that we can actually do a signal generator as a fact, fully edible. We can couple with our battery because this is fully edible and is actually able to provide a signal. And in the next step, we need to integrate the system to create the pill. We want to make a pill for gastric acid detection. So we really believe that it can have an impact on gastrointestinal motility disorder, for example, et cetera, et cetera. And I think this is all from my side. And I want to thank Mario Caironi, which is my boss of my group, and you all for your kind attention. Questions? One brief, but we have to.
Do we have one question for the interesting? Yeah, go. Yeah, I also have.
I'm here, by the way.
Yeah, exactly. You go and I can go after.
Well, it's a long story. Synthetic response, the silicon works much better. Organic is ongoing, is good enough, but we have a different approach in this case. So we believe that we don't need to make a computer into the pill. We really need to provide some very simple function. We need one brain external and thousands of sensors. This is what we need. So we may tune the functionality depending on what we really need to do, and to the power. Also, we prefer to have low power here because we don't want to damage the intestine or to be dangerous. So as a fact, maybe a good application of organic electronics. Okay, thank you guys.
Thanks a lot.